Welcome to High Voltage Engineering channel. My name is Mohammad Qafarian Yasar, and the title of this video is Why do we use high voltage to transmit electric power? So first I'll say a few words about production and consumption of electricity because it's relevant to this title, and then we analyze this question in detail. Okay, so let us consider a country. Here I have the map of Sweden. The three red dots are the major cities of Sweden. We have Stockholm, Gothenburg, and Malmö. Approximately 25% of Sweden's population is located in these three cities. If you look at electricity consumption by sector, we see that industry, households, and services are the major consumers of electricity, and these are present in a city. So we can say that large cities are the major consumers of electricity. Now, if we look at the map again, we see blue dots. These are hydropower plants spread across the country. And most of them are located in the north of Sweden because we have a lot of water resources there. The yellow dots are the nuclear power plants, and the green dots are the major wind farms. We have smaller wind farms and the smaller hydropower plants, which I haven't put them on this map. One thing that we can notice is that a large consumption site like Stockholm is located tens of kilometers or maybe hundreds of kilometers away from the production site. So we have to transmit electricity over a very large distance. And this is very important in answering the main question of this video. So as we can see, there are many production sites, consumption sites spread throughout the country, connected by transmission and distribution lines. So the system is really complicated. If we want to analyze a particular situation, we usually don't model the whole system. Instead, we use smaller scale standard test systems. Here I have IEEE 9-bus test system. These are the buses, and in total we have 9 buses. There are 3 generators. We have 3 transformers, few transmission lines, and then we also have loads. So these are loads, consumption of electricity. So depending on the complexity of problem you want to analyze, you may use 9-bus system, you may use 14 bus, 30 bus, 118 bus, and so on. In our case, we don't need to go that far. We can use the most simplest system possible, which is 1 generator and 1 consumption site connected by a transmission system. So here I have a generator, transmission line, consumption sites. So I want to analyze 2 situations. One is we transmit power at low voltage, and in the other case, we increase the voltage by this transformer, transmit the power at high voltage, decrease the voltage, and deliver to load. So in one case, we transmit power at 220 volts, and in the other case, we transmit power at 22 kilovolts. One thing that we know from the discussion is that the length of this line may be tens of kilometers, maybe hundreds of kilometers. The other thing that we should know is about the amount of consumption that we have here. To have some idea about the amount of consumption that we have here, let us look at the following information. Average electricity consumption per household in Europe is around 4,000 kilowatt hour per year. Here I have information of Technical University of Delft, which has around 25,000 students, 5,000 staff members, so totally 30,000 people. And the average consumption is approximately 68,000 megawatt hour per year. So if I take this much of energy consumption and divide it by number of days and number of hours, we see that on average we need 7.5 megawatt of power. Now obviously, because the load varies during the day and during the seasons, if we want to really provide the university with its need, we need to have a much more capacity than this 7.5 megawatt. But here let us assume that we have a consumption of 7.5 megawatt. So the problem that we have formulated is that we have a university which has 30,000 people. The consumption is 7.5 megawatt, and it's located 10 kilometers away from the production site. So we want to transmit power once at low voltage and once at high voltage, and we compare the two cases. Here we have the formula for power transfer in a three-phase system, which is the square root of 3 times line voltage times line current multiplied to power factor, which is this one. Now for simplicity, let us assume that power factor is 1. So we take that from 1. And now I instead of writing V line and I line all the time, I just write V and I. So in order to transfer a power P, we can take, we have this formula, square root of 3 times VI. And now, if we want to calculate the amount of loss that is created in transmission system, we have 3 phase multiplied by the resistance of the line multiplied by I power 2. As an alternative, we can increase the voltage 2 times, but instead we can decrease the current 2 times. These products, all of them are equal to the previous one, so P is the same in these two cases. But if we look at the loss in transmission line, we see that again we have 3 times Ri2, but because I is half, so the total loss would be a fourth of the previous one. Or alternatively, we can increase the voltage 4 times and reduce the current 4 times. So in this case, the loss becomes 16 times less. So it is now very clear that why we increase the voltage level. Because by increasing the voltage level, we can actually decrease the current through transmission line, and therefore we can reduce the ohmic loss in the transmission line. Now, some of you might be confused that why do I use this formula to calculate loss? Why I say it's Ri2. If you look at the simple circuit that we have here, we can say that the loss in this resistor is Ri2, so this is okay. But we have also another formula that we can use to calculate loss, and that is V2 divided by R. Now, in this case, if I use this other formula, like, okay, loss is 3 times V2 divided by R. In the second case, loss is 3 times V2 divided by R, but V is here 2V. So the loss here should be actually 4 times than this previous case. The important thing is that when we use this circuit and these formulas, here we have voltage directly across this resistor, and in this case we can use this formula. In the problem that we are solving, the voltage is not actually across the transmission line. The voltage is on the transmission line, so this V is not really across the resistance of transmission line, so we cannot use this formula to calculate transmission loss. So these two, we cannot use it. So in order to calculate loss, we have to go through these formulas, and we can see that as we increase the voltage level, the amount of loss decreases. Now, okay, so if we have a transmission line which has a certain amount of resistance, and there is a load which has a resistance R, obviously there would be also a voltage drop across this transmission line. So let us assume that there is no inductances and no capacitances for simplicity. So if we send the voltage at voltage V, at the receiving end, we receive the voltage V minus delta V. And this delta V is whatever voltage that drop over transmission line. If we want to use this formula, V2 divided by R, we actually have to use this delta V. In that case, it will work fine. But anyway, it's not important. One thing that is important is there is a voltage drop across line. And this is actually another issue that we will see in the next slide. Okay, let us consider a three-phase transmission system. Here is one of the conductors with the cross-section A and the length L. So the length is 10 kilometers. If we calculate the resistance of this conductor, we see that it's length divided by conductivity multiplied by cross-section. So the length we know is 10 kilometers. The cross-section I took 5 to 5 centimeters. This is actually a very large cross-section for 7.5 megawatt of power, but here I just took it. And this is the conductivity of aluminium. If you just multiply everything, calculate R, then you see that the resistance of this conductor will be 0.10. Now, if we calculate the current through the conductor, we know how much power we want to transfer. It's 7.5 megawatt. We know the voltage, which is 220 volts. The line voltage is 220 volts. So the line current would be 20 kiloamps. If we calculate the loss through this transmission line, we have 3 Ri2, do the calculation, we get 120 megawatts of loss. So in order to deliver 7.5 megawatt, actually we lose 120 megawatts in the transmission line, which is obviously not acceptable at all. Now there is another issue, and that is related to the voltages. So here we have the receiving voltage, which is 220 volts. We want to keep that voltage as stable as possible. Now, the sending voltage is actually the receiving voltage plus the voltage drop over the transmission line, which is Ri. If we do this calculation, so 220 plus this, then we see that at the sending side, we need a voltage of 2220 volts in order to deliver 7.5 megawatts at 220 volts at the receiving side. Now, during night, the amount of load here decreases. This means we need less current through transmission line. In order to keep the voltage here 220 volts, then because this current has decreased, then we have to actually decrease the sending voltage. So if there is no load, then this is 0. So the sending voltage should be only 220 volts. And if it is, let's say, only 2000 amps, not 20,000, let's say if it is 2000 amps, then the sending voltage should be, this becomes 200 plus 220 is 420 volts. So we see that we have to regulate the sending voltage within a very large span in order to keep the receiving voltage stable close to 220 volts. This is difficult to regulate the voltage within such a large range. Now let us consider the second situation, in which first we increase the voltage level to 22 kilovolts. We transmit the electricity over this high voltage level, and then we reduce the voltage to 220 volts and then deliver the power to the consumption site. So in this case, if we calculate the losses, they calculate the current through the line, we see that the current would be only 200 amps. And if we calculate losses after that, we do this calculation and we see that the losses is 12 kilowatts. So we deliver 7.5 megawatts and the losses in the transmission line is only 12 kilowatts, which is very acceptable. It's actually much less than in reality. And the reason is that first, the cross-section that I consider here is very large for that power level, for 7.5 megawatts. And the second thing is that there are also two transformers here, which each of them has also some amount of losses, which I haven't considered in this calculation. Now, if I calculate the voltage at the sending side, the same as before, it's the voltage at receiving side plus the voltage drop over transmission line, which is Ri. Now, voltage at the receiving side is 22 kilovolts, and the current is 200 amps. Do the multiplication. Then the sending voltage should be 22,020 volts. Now, even during night or whenever that the load is very small, even if this is completely zero, the sending voltage would become 22,000. And during the full load, in this case, is 22,020 volts. So the regulation for the sending voltage would be very small. And so we have seen two advantages for using high voltage transmission lines. One is, of course, reduction of losses, and also the regulation of voltage would be much easier. So now you might ask the question that why don't we use very high voltage levels for all transmission lines? We have discussed that using higher voltage levels decreases the amount of losses. So why shouldn't we use it? Now here we have to look at the cost problem. The total cost of a transmission line includes initial investment and the running cost. So the running cost is basically mostly due to the losses and also due to the maintenance and repair. Now if you look at this yellow line, this is the low voltage line that we have discussed. So the initial investment is small because we do not have transformers. The transmission line does not need high isolation levels. We don't need large towers and so on. But as you can see, the running cost is very large. So the slope of this line is very sharp. So every year, the total cost of the line increases and increases because we have a lot of power lost. Now, if we increase the voltage, let's say we take the green line, which is this 22 kilovolts line, then initial investment would be more. But then the amount of losses would be less. So the slope of this line is smaller, and therefore after a while the total cost of the line together with losses becomes less than the first case. Now if I build a transmission line that is like 500 kilovolts for this 7.5 megawatts, then the initial investment has to be very large. We need to build substation, huge transformers, and very large transmission lines. So the initial investment is very large. Even if we don't have any losses, during the normal operating lifetime of the transmission line, which here I put 50 years, this line would be still more expensive than the other one. So it's not worth it to make very high voltage levels, even though the losses is less. Okay, so here we get to the end of this presentation. A topic that I could answer within 5 seconds. Now I managed to talk 15 minutes about it. Have a nice time and bye.